Now I've said multiple times that the entropy is a state variable. It does not depend on the path taken, only on the initial and final states, or the change only depends on the initial and final states, and we can in fact calculate an actual value for the entropy for any given state. Proving that it's a state variable really requires many very careful experiments to show that whatever process we use to go between two states, the total integral of dq over t is the same. Remember, this is a straight t, so it needs to be in kelvins. However, it turns out that in one particular example, we can actually integrate dq over t directly without any reference to the process, thereby showing that it is in fact a state variable. That situation is an ideal gas. We know from the first law of thermodynamics that E internal, or the change in internal energy, is equal to the heat minus the work. So the heat is equal to the change in internal energy plus the work. Well, the change in internal energy for an ideal gas, we've already learned, is just the number of moles times the specific heat at constant volume times the change in temperature. And the work is simply the integral of P dV. Well, let's put this into an integral form for all of these parts. So dq is equal to n CV dt plus P dV. Let's shrink this down and get a little more space. Now we divide everything by temperature. So that becomes the entropy integral. Now if we look here, before we divided, P dV was entirely dependent on process, and dq was therefore dependent on process. It seems like that's still the case, but let's replace T by whatever we can get from the ideal gas law. We know that PV equals nRT, so T is equal to PV over nR. Let's plug that back in here, and what I get is that dq over T is equal to n CV dt over T plus P dV times nR over PV. Notice P cancels, the nR will pull out the front, and I'll have dV over V. So this simply means that ds is n CV dt over T plus nR dV over V. Well, now I can integrate everything. If I integrate from an initial to a final state, I just find that the change in entropy is n times the specific heat at constant volume times the natural log of T final over T initial plus nR times the natural log of V final over V initial. Neither one of these integrals required that I know the path. As a result, this delta S is independent of the actual path I take, and therefore S itself, at least for this limited situation, is a state variable.